Earth is a riot of colors. From the blue oceans and the oozing red-yellow lavas, to the multi-tone browns and off-white mountain peaks, the planet boasts nearly every color under the sun. But there was one color which stood out more than most, and it's what makes the Earth so special: the color green. It signified that our planet was ready for business and was on a magical journey of evolutionary discovery. There was no time more important for the expanse of greenery than 350 million years ago, a period known as the Carboniferous. During this time, the Earth had an average temperature of 20 degrees Celsius, nearly 10 degrees hotter than it is today. The lands were covered in vast, lush green forests and swamps, which removed huge amounts of carbon dioxide from the atmosphere. The atmospheric oxygen levels peaked around 35%, compared with today's 21%. As a consequence, giant creeper crawlies now emerged. The size reached by insects and similar creatures is thought to be limited by the amount of air that they were able to breathe. Deadly poisonous centipedes, some 6 feet in length, crawled in company of mammoth cockroaches and scorpions as much as 3 feet long. Most impressive of all were dragonflies that grew to the size of seagulls. One exquisitely detailed fossil of a dragonfly that died 320 million years ago shows that it had a wingspan of 2.5 feet. And alongside these magnificent creatures, flora and fauna thrived in the heat of this environment, some trees reaching 50 meters tall in as little as 15 years. The Carboniferous period marks one of the most important intervals in Earth's history. Over 60 million years, nearly 100 million tons of organic matter would be buried year on year, storing vast amounts of carbon into compacted layers of peat and eventually turning into coal. But something happened at the end of the Carboniferous that stopped this process. The amount of coal deposition declined dramatically and never recovered to the same level. What caused this change? Well, sit back and relax, because this episode's going to be interesting. I'm your host, MrEarthGuy, and you're listening to Earth SciShow. Coal is composed of the fossilized remains of plants that lived millions of years ago. The reason coal is so prominent from this period is due to the presence of lignin, which is a complex polymer that gives wood its strength and rigidity. See, lignin is very hard to break down. In fact, it's one of the most abundant organic molecules on Earth, second only to cellulose. Most organisms can't digest lignin, so when these ancient plants died, they were piled upon the floor, formed thick layers of organic matter, and over time, these layers were buried so deep in sediment and compressed by heat, turning into the coal. So what stopped this process dead in its tracks? Well, the answer may lie in the evolution of a group of fungi called white rot fungi. These are the only microorganisms that can break down lignin completely, using special enzymes that can cleave the bonds between its subunits. White rot fungi are common today, and you may have seen them growing on dead wood or fallen logs in the forest. A new study published in Science in 2012 suggests that white rot fungi evolved at the end of the Carboniferous period, and that their emergence coincided with the decline of coal formation. The study was conducted by a team of 71 researchers from 12 countries. They compared 31 fungal genomes to reconstruct the evolutionary history of lignin degradation. The study found that white rot fungi belong to a large group called Agaricomycetes, which also includes mushrooms and other wood-decaying fungi. The oldest ancestor of this group was a white rot species that had multiple lignin-degrading enzymes and lived about 300 million years ago. Many surviving lineages of Agaricomycetes still produce these enzymes today. But some lineages lost their lignin-degrading abilities as they adapted to different lifestyles. For example, brown rot fungi can decay wood by breaking down cellulose and hemicellulose, but not lignin. They leave behind a brown residue that is rich in lignin. Other forms, like mycorrhizal fungi, form symbiotic relationships with plant roots, helping them absorb nutrients from the soil without harming them. The study suggests that white rot fungi were the first organisms to be able to decompose lignin completely, and that they had a major impact on the global carbon cycle. By destroying lignin, they freed up cellulose for their own consumption and also released carbon dioxide back into the atmosphere. They also prevented large accumulations of woody debris from being fossilized as coal. So, if it was not for this white rot fungi, we might have more coal deposits today and our entire atmospheric composition would be different. It is without question that white rot fungi helped us end the coal age, closing the Carboniferous period. But due to its capabilities, we may also use these fungi to help us transition to a more sustainable energy future. That's because white rot fungi have another potential use: biofuel production. Biofuels are renewable energy sources derived from organic matter such as plants and algae. They can be converted into liquid fuels that can power vehicles or generate electricity. One of the main challenges of biofuel production is breaking down plant biomass into simple sugars that can be fermented by yeast or bacteria into alcohols or other fuels. Plant biomass consists mainly of cellulose, hemicellulose, and lignin, which form a tough matrix in the cell walls. Lignin doesn't degrade very well and blocks access to cellulose. White rot fungi have enzymes that can break down this lignin and release cellulose from the cell walls. These enzymes could be used to pre-treat plant biomass and make it more accessible for further processing. Or alternatively, white rot fungi could be used directly to ferment plant biomass into biofuels. White rot fungi are not only good at breaking down lignin, but are also breaking down other complex organic molecules. White rot fungi are amazing organisms that have shaped our planet's history and may shape its future as well. They are part of a diverse and fascinating kingdom of life that we are only beginning to understand. So next time you're wandering through a forest and you see a fallen tree, and if it's covered in white specks of fungi, just remember how important that particular organism is in shaping our planet, and if it wasn't for that fungi, we probably wouldn't be here today. Over the course of 300 million years, this organism has shaped and changed the narrative of evolution on this planet. It's also altered how our atmospheric composition is and was, and it will continue to do so. And that's it for this episode. I hope you found it really interesting and you learned something to take away and talk about with your friends and family. You've been listening to Earth SciShow, and I am your host, Mr. Earth Guy. And remember, stay curious.